Yeah. There we go. Yes.
Yay. Thanks a lot for the kind introduction and also for the invitation. So I'm very much looking forward to having some very lively discussions as hopefully as most of the times. Yeah, so Nick already told you about the question, who should help whom? So most people, if they think about robots, they would think about robots supporting us with the tedious or dangerous tasks. And then there are the annoying cases where the robot does something wrong or gets stuck, and we also have to help the robot to get unstuck. And then in a similar vein, who should teach whom? Depending on what kind of research you're doing or what your perspective on robotics is, you might say, yeah, it could be a great idea to actually use a robot also as a teacher for humans. My research focuses more on teaching robots new tasks. So that's an example of kinesthetic teaching, where a person shows the robot how to solve a new task. And in this talk, what I'm going to focus on is how do we actually make this teaching in interaction with a person as smooth as possible and as efficient as possible for the robot. So there are largely two different but complementary ways on how robots can learn new skills. So if I say skills, I'm talking about learning some kind of movements on the order of a few seconds or a few minutes. And the first one is imitation learning, where a teacher demonstrates a skill and the student then tries to mimic that, like we also saw on a previous slide. Here's an example from my own research, a bit older, where Simon, my former PhD student, demonstrates the robot how to unscrew a light bulb and then how to put it in a trash can. So here, yeah, you need a couple of turns to get it loose, and then you move it to the trash can. So just playing back this recording, that's not really interesting. What we're really interested in is to generalize the movement. So for instance, in this case, for the number of rotations you need to do to unscrew it, but you could also think about changing the position of the light bulb holder or the trash. And in particular, what we were interested in here is the order of little sub-movements you need to do. So you need to move towards the bulb, then grasp it, rotate it in one direction, and so forth. And then you can represent that as a form of a graph that tells you in which order you need to do things. And then what we were also interested in is, okay, when do we actually switch to the next primitive? And then the robot can reproduce that and also generalize to new situations. So here you see it unscrewing, and then when it becomes loose, it's pulling slightly on the bulb, so it can actually remove it. So that's really important to detect it accurately, otherwise the light bulb will go flying. Okay. So then it successfully did that. So that's an example of imitation learning. And the other side is reinforcement learning, as you can imagine. Like for us, if the task gets slightly more complex, also a robot needs to practice. What I'm going to use a bit as a running example is ball in a cup. So that's a little game where you have to catch the ball in the cup. And here's my cousin's daughter. She was around 10 back then. I showed her once how to do that. And then it took around 35 times until she caught the ball in the cup. So reinforcement learning is learning by trial and error and trying to maximize a reward. And you can see the little reward, the chocolate here. Okay, so in both examples I showed you, you have the human in the loop in some form or other. For the imitation, it's very clear. You have the human demonstrating and then the robot mimicking. But also for reinforcement learning, you need to define the reward function, some kind of function approximation, how exactly you set up the problem, and so forth. So to illustrate a little bit what we did there is the reward is more or less based on the distance between the ball and the cup. The first time the robot tries, it's still a bit far, so it gets a pretty low reward, close to 0. Next time it's a bit closer, so it gets a bit higher reward. And if you imagine that you do some kind of weighted combination of the two of them, you might get something that's already pretty close, and then in this case bumping on the rim of the cup. And then the maximum reward would be a 1 in this case, so it's already pretty close. And then if you repeat that, so mainly focusing on the good one and only the other two a little bit, you can hopefully catch the ball in the cup very quickly. So that's the robot trying out different things and then seeing what works, what doesn't work, and adapting accordingly. Also here we help the robot additionally by giving it an initial demonstration. So here there was a good demonstration, but then as the dynamics are a lot more complex here, if you just play that back, then you miss the cup by, I don't know, 10, 15 centimeters. After 15 trials or so, it's already considerably closer. Now the next one I think goes a bit too far. And then it's going to hit the rim of the cup. And then finally, after 60 trials or so, it starts to get the ball into the cup. And after 100 trials or so, that has converged and works very reliably. Okay, so as you can see in the dates, that's some fairly old videos. What people are working on nowadays is doing end-to-end learning. So we had some vision system that tells us where the ball is. We used low-dimensional representation and so forth. If you then not use neural networks to try to learn end-to-end, that usually means you need some form of big data or some other tricks to do that. So in this famous example here, that's from Google, they had an army of robots working day and night for a couple of months, actually nonstop, just to learn to pick up simple objects in bins like that. So that's clearly impressive, but not really desirable or practical in any sense. Okay, so what I showed you so far is the human is involved in the beginning, either giving demonstrations or setting up the problem, and then the robot is off on its own trying to learn something. Now, if you again compare it to how humans learn, you'll actually notice that there's often a continued student-teacher interaction. So while somebody is learning, you might provide additional demonstrations or some other form of intermittent feedback. And at least nowadays, that's still largely missing in robot learning. And I believe that including these intermittent interactions with a teacher allows you to speed up the learning, which in turn allows the robot to solve more complex tasks. And that's also a somewhat intuitive way for humans to teach. And in the remainder of the talk, I'm going to show you a few examples of that's what I'm claiming here is actually hopefully true. Okay, so how does this interactive learning look like? We have a robot and an environment. The environment has a state, so it could be the position of the robot in the world or the position of the robot arm. And the agent has a policy which tells it which action to take for each state. So depending on where it is, what to do. And that's just more or less a traditional control loop. Now what we have additionally is a teacher. And the teacher is going to observe the state of the world and the robot, potentially also what action the robot took. And then there are many different variants you can think of. But in some form or other, the teacher is going to provide additional information to the agent. Usually if something is going wrong, so it could be an additional demonstration to show something that the robot hasn't seen yet. Could also be just a correction on how to modify the robot behavior to perform the task better. So in the first few things I'm going to show you, we're going to focus on corrections in the action space. So the teacher very explicitly tells the robot, okay, you should have moved a bit faster or a bit slower in order to perform the task well. To come back to the example I had before, the ball in a cup. So here you see the same thing. However, now we start learning from scratch, and Carlos, my postdoc, is sitting in front of the computer and occasionally giving it some additional feedback. So in this case, move more to the left, move more to the right, move slower, move faster. And then after 17 trials or so, it's already quite close. And then let's see. Next one. So that's after 25 trials or so. It can successfully catch the ball in the cup. So compared to the human child, it was around 35 times. If you ask an adult, it's also usually around 20 times. So it's really the same order of magnitude now. And if you compare that to learning the skill from scratch, so without initializing it with imitation learning, just using reinforcement learning, that takes 2 orders of magnitudes longer. So some 2,000 or so trials usually in our experiments. And that's still not doing end-to-end learning, but relying on low-dimensional inputs for the states. Okay, so that directly brings me to the next part, learning from high-dimensional inputs. So in this case, from raw camera images. Typical thing you're going to see in deep learning is some form of encoder-decoder structure, where you have the high-dimensional images here. You bring it back to some kind of low-dimensional representation that hopefully still contains all the relevant information. And in order to train that, what you typically do is you decode it again, and then you try to ensure that the output matches the input, so that effectively here this low-dimensional representation contains all the important information. And then once you've trained this mapping from the camera images to a low-dimensional representation, you can use that to learn the robot behavior, so the policy on top of that. So then you would remove the decoder part and then start learning the policy, either completely freezing this part or maybe also training that partially. So you could do that beforehand. So you collect lots and lots of data of images the robot is going to encounter, and then try to find some kind of generic representation and then learn a policy on top of that. So that's what we see here. But as you can already imagine, that's probably not the smartest thing to do, because depending on the task you do, some stuff in the environment might be relevant and some other stuff irrelevant, and that might change completely depending on which task you want to do. So then the obvious thing is, okay, so can also learn that this representation while the robot is learning the task. And that's exactly what we tried to do there, to learn simultaneously an embedding and the policy. And then, so really the main objective you want to do is to learn this policy, so the actions the robot takes. But then as an additional criterion, we have this reconstruction from the input image to, in this case, a slightly blurred image of a tree again. And again, while this whole learning is happening, the robot is going to get feedback from its human teacher. Not continuously, so we are not remote controlling it, we're not teleoperating it. It's just the teacher is jumping in occasionally to fix some things. So what you see on the left is the reconstruction, so based on the low-dimensional representation, and then you can see that already very quickly it learns something that represents the real images reasonably well. And again, what you can't see in this video is the human teacher occasionally giving feedback via a keyboard, in this case, on what the robot is supposed to do. In this case, push this whiteboard swiper thingy off the table. And then let me skip forward a little bit. And that's in real time here, so we can learn that really in a couple of minutes. Come on. Nope. Okay, let's see. Here's another example of teaching this little ducky town robot to drive. And that's Rodrigo, one of my PhD students, and you can see him holding the keyboard. And if you look very closely, sometimes he presses buttons to teach it how to drive. Again, here the raw camera images and the reconstructed images. And again, after just 10 minutes or so, it learns how to drive on the correct side of the road. And then here, that's in real time. And here you can see that it really learned and that he's not using the keyboard any longer to control the little robot. Yeah. So that's not just taking the images, compressing it down to something useful, and then doing control on top of that. However, for many tasks, you need some kind of memory. So you need to, so either if you only can observe the images, but you need to know the velocity, then you need to have at least a couple of images, or you might act based on something you saw in the past. And for that, we can have a very similar structure, but here additional a recurrent unit in a neural network. So here a couple of toy examples. I'll skip over those pretty quickly. Here the agent only observes the images, but not the velocity. But in order to solve the task, so for balancing this pendulum, you really need to know how fast it moves. And here we compare two different methods. The one on top, that's our method where we use corrective interactions. So we give corrections in the action domain. And on the bottom, that was a different approach where you need to give additional complete demonstrations, which is typically a lot slower. Okay, so that's again the reconstruction and the images. And then here it's a little real setup. And that's to demonstrate that it's really learning to do the control based on the images and not based on some internal states. Wait. Come on. And then here, a corresponding robot experiment. We have the camera input. The only thing the robot sees is this shaded white area there. So it needs to touch the fake oranges. So it needs to remember, okay, the orange was here and it's going to move there in order to then touch them later on. And also something like this we can learn in 5 minutes in this case to right. And then here, if you train it longer, after 45 minutes, it can really do it very accurately. I'm not sure if you can see that here. Here again, you could see somebody doing the teaching. Here you see it nicely with the keyboard. And here the task is to touch the oranges, but avoid the pairs. Because we already trained a good representation, so going from the camera images to a compact representation, teaching this additional task is something that can really be done within 10 minutes. And if you compare that to a more traditional deep learning end-to-end approach without having a teacher in there, we haven't tried just because based on the toy examples we saw, that's again taking at least an order of magnitude longer. So think about spending a day teaching something like that. And the other big problem is if you use these other methods, you need to know beforehand what kind of data is required. So it's really up to the human demonstrator to think beforehand, okay, that's the situations that could arise. I need to collect data for that. I train the system, you test it out, I figure out it doesn't work. I need to collect more data, and that typically is a couple of iterations that are required for that. Okay, let's see. I have a couple of questions. Nick asks if do you want to just ask directly?
Sure. So, I actually question, like, so do you assume that the human corrections are more or less optimal, or at least like work towards more reward? But and also, what happens if the human correction is actually not helpful at all? So how can you take that into account?
Okay, so we assume that the human corrections are at least somewhat helpful. It's not a problem if they are wrong or the human changes his or her mind. But if the human is just demonstrating nonsense, then depending on which setting you talk about, in the imitation learning, if it's really purely learning based on these demonstrations, then obviously it has no chance whatsoever. Then it's just going to learn whatever you teach it. In the other example I showed where we combine it with reinforcement learning, it's very unclear what's going to happen. It really depends on how you set it up. The robot has the chance to learn it correctly based on the reward you have defined, and then how much the human input hinders the robot is a different question. If it's at least something more or less sensible, so it might not be the correct task, but showing something like you're not supposed to move very erratically and shaky, but smoothly without showing the actual task, that might be helpful. Well, you can come up with the other scenarios where it's really going to harm the performance. Okay, Luciano.
Yeah. So so my question goes a little. I was thinking this is like one step further. If you teach like a human teaching a robot, but assuming that the robot is teaching another robot, and let's think about like, I don't know, some scenario of a warehouse. But of course, if the same robot with same joints, okay, they could just transfer the learning. But let's assume that the robots are different. As we from humans are different from the robots, the robot is teaching another robot that's a bit different. So then I'm thinking, of course, that could scale up, and then some emergent phenomena could come there, because if you didn't really learn this as 100% and you teach someone else, yeah. So how do you see? And there's some alternatives. Do you think like more imitation learning, reinforcement learning? How could we tackle this kind of issues?
Yeah, good question. I don't have a definite answer on that. So it really depends on what you want to teach or what you want to transfer. So if you, I'm going to get to that in a second. So if you, okay, I'll just show that on the slides because that nicely collects to what you were asking.
Yeah.
So what I was talking about so far was teaching in the action space. So directly, in this case, in the 7 joints of the robot, and then saying which velocity, for instance, you should apply, which is kind of very direct and low level and probably allows you to very much optimize the movement. However, it's typically pretty high dimensional, and at least for humans, it's non-intuitive. Connecting to your question, it doesn't transfer to a different embodiment at all. Well, if you consider the state space or the task space, so for instance, the position of the end effector, then that's something that you could transfer. So if you know the trajectory of the end effector, then it doesn't really matter how the kinematics of the robot, as long as it has kind of the same workspace, obviously.
Yeah.
And depending a bit on the constraints it has, but that's something that's a lot easier to transfer. And arguably, that's also a lot more intuitive and easier for a person to teach that isn't familiar with the robot. The downside then is that you still need to translate that into the movement of the robot. So the actions, again, using some kind of inverse kinematics, so dynamics models, which might be as themselves a bit tricky to learn. So to come back to the question, so if you have robots with different embodiments, thinking about at which level of abstraction you should transfer is definitely one thing that's done. So for instance, transferring trajectories in end effector than in joint space would help. the big advantage robot to robot teaching would have is you can work around the communication issue a lot better. So you have complete knowledge on both sides effectively. So I would say better ways of doing that compared to what I was presenting here, which really also focuses on, okay, a human doesn't really know exactly what he or she should do. They don't like to kind of be constantly teleoperate the thing, but it's a lot more pleasant if you only need to jump in when something goes wrong and occasionally give feedback. You really care about how long it takes. So for robot teaching, you can probably do a few other things that might be better. So yeah, you could probably apply those methods. I'm not sure if they're the best.
Yeah. Okay. Thanks. Yeah.
Okay, and then what did you have? How could we keep human control?
Yeah. I was thinking like if you teach, but you don't teach like 100%, the robots don't learn 100% what you mean, and then they teach someone that doesn't learn 100%. So you gotta increase the gap as far as you go from the original source.
How is that called? That stupid game where you whisper in somebody's ears and then you do the chain?
Yeah, exactly.
The telephone game, I think, right?
Chinese whispers.
Chinese whispers, yeah, exactly. So you would get something like that, indeed. Yeah. So yes, to be totally frank, at the moment, very much looking into the question: how can robots be best taught by humans? And it's a bit more on the algorithmic side. So we're looking into how humans experience the teaching, but it's not like we're at the moment looking into human-robot interface design, so to say. And then what you're saying, that adds a whole new additional layer of complexity on top of that. Definitely very interesting, and we should get there. Okay, what else? So Wendelin asks, do you want to unmute and directly ask?
Sure. So I was just like referring to the discussion before. So if the robots, or the first question is like, the robots still get the original environmental reward, right?
Yes, in the reinforcement learning case.
So would this just mean that if you have a robot that trains another robot, after a while, that other robot would still converge to the original task? It just may take longer because the first robot might have given him some bad ideas?
Could be, yeah. Yes, I mean, that's the general question in all transfer learning approaches. When is it actually beneficial to transfer, and when is it better to learn from scratch?
I mean, like it's very different from transfer learning, because in transfer learning, like, for example, it's very different from imitation learning. In imitation learning, you don't know what the real task is. But in this case, I think Luciano's concerns should not be too hard to disprove, because like basically you still get the original task, so you can't really stray too far away from that.
Yeah, I agree. I mean, so I've been presenting two different things. Some of them were purely based on imitation learning, so supervised learning, where you don't have that, and there kind of this drift could very well occur. But yeah, I agree. If you think about reinforcement learning and transferring the reward function as well, then yeah, worst case is it takes longer to converge to that.
Okay, thanks.
Okay, good. So here I was just introducing that we might actually want to teach the robot in state space, so in the end effector space in this case. And in this drawing I have here, that's pretty obvious because that's something that's already provided more or less by all robot manufacturers. But in some other cases, that might not be so obvious. So I have another little example here. Where's my mouse here? That's a laser pointer on the robot, and it's trying to write a letter on a whiteboard, just a little fun task where we actually don't know the model of the complete system. And we actually need to learn it at the same time as learning the task. Or you could say, before we do the learning, somebody sits down for half a day and writes that down in order to program the robot to be able to be controlled in task space. So in this case, what I mean by task space is what you would like to do is to directly control the position of the laser pointer point on the whiteboard and not care about how the robot actually is supposed to move. And the approach Snehal came up with actually allows to learn that simultaneously. So learning the mapping from the task space to the robot actions and actually how the task is supposed to do. Again, using interactions. And here, that's one of the initial things where you still have lots of corrections from the human teacher. In the top right, it's just a zoomed one, and we enhanced the laser pointer. And then here, after 15 minutes, it again learned to do that, and the last move you saw here is the robot doing it autonomously. So here it's writing core, the name of our department, which nicely coincides with the first 3 letters of the conference where we published it. Okay, so far what I was talking about was very much on the level of directly controlling the trajectories, if you like, of the robot. In the very first example I showed you with the light bulb unscrewing, it was on a higher level where we were considering the sequence. So for learning these kind of things in a sequence, what you will quite often have is different reference frames. So that if you say you have an object and you attach a reference frame to that, the robot can move relative to the object rather than moving in world coordinates or in absolute coordinates, which then very much helps to generalize to no matter where you put the object. And if you start having more objects, then suddenly you get a whole lot of these reference frames or coordinate frames. So in the light bulb example, we would have the light bulb, the holder, the trash bin, maybe world coordinates additionally. And then one of the challenges for the robot is to figure out from the demonstrations which is actually the relevant coordinate frame. So should I move relative to the light bulb or the holder, or should I actually use position control, or should I use force control? So here's another example of that, where the robot is picking up this mug, and we have 2 coordinate systems. One is relative to this coaster, and the other one is relative to the cup. And now if you only give one demonstration, when the cup is on the coaster, there's just not enough information in the data we collect for the robot to figure out what it's supposed to do. You could put in some prior, okay, we're going to touch the cup, so that's probably the one we're interested in, and then use that. but you can do that, but that breaks down pretty quickly because these priors tend to be somewhat specific. So now if you always have the cup on top of the coaster, that's not a problem. It will work fine for either reference system because it's always just a little offset, and no matter how you describe the movement, it's going to result actually in the same position. Now, if you separate them, like we have in this example here, then suddenly that becomes interesting. And the robot needs to decide on what to do. If it's purely based on the initial demonstrations, then there's no way it can do it other than flipping a coin. If it can ask for feedback or have interactions with the teacher, then that's something that is easy to resolve. And what we were additionally considering here is, like I described before, in some cases you actually don't care about this ambiguity. So it's fine if you don't know which of the two you want to use, because it's going to result in the same movement. And you don't want to bother the human teacher if it doesn't really matter anyhow. So the approach we came up detects if there, well, obviously, if there's still multiple reference frames possible, if it's actually relevant in the situation we're currently in, and then if it can't decide on its own, or if it's actually relevant, only then the robot is going to request feedback. Okay, so that's the corresponding video here. The demonstration was already given. So let me go back. That was way too quick. So we demonstrated picking up the cucumber, moving it to the lower tray here. So if it's in the same position, then that works fine. If we move the cucumber only, that's also fine because we touched that and we know that it's going to be relative to the cucumber. Okay, so then we can remove that. Works fine. Now what happened is we switched to two crates. Now you have an ambiguity. So were we interested in moving relative to the world coordinates, so the absolute position somewhere here, or are we actually interested in the crate? And what you're going to see now is that it starts moving and then it stops because it's unsure, which is kind of the trigger for the human teacher to give feedback. In this case, it's a haptic kind of little push in the right direction, which then helps the robot to disambiguate that. And from now on, it actually knows, okay, we're not interested in the absolute position, but in the crate position. So it discards that from its decision tree, so to say, and from now on has learned how to act in these situations. Okay, can make it a bit more complex if you have multiple reference frames attached to the two sides of the object, of this box, I mean. And then again, the question is, should we move relative to that one, or are we actually interested in the one that is bang in the middle between those yellow and red coordinate systems? So here you see a different form of interaction via some kind of on-screen yes/no interface. So I was asking the yellow one, and Giovanni said no. The Apple one also no. And then the only remaining possibility was something in the middle. So here's one last task where we're supposed to stack boxes on top of each other. And based on that, we also did a little user study with 12 people, I think, just before the lockdown happened. So here the task is to stack one specific box of tea bags on top of another one. Here you see the kinesthetic demonstrations, and what we compared here is purely doing it with these demonstrations versus having the interactive corrections, or the robot actually asking for feedback if there's an ambiguous situation. And as you can already see, if you've not done that before, teaching it like that is also not so easy, time consuming and annoying as well. So you need like 6 demonstrations to get all the combinations covered. Well, if we do that with the interactive method here, you just get 1 initial demonstration. And then only in some cases, it's not going to know what to do, and then going to ask for, again, feedback by getting pushed. So that's significantly quicker to teach for the human and to learn for the robot. And also in terms of mental demand, physical demand, temporal demand, if we ask the participants, they very much prefer to teach it in this interactive, corrective fashion rather than just giving a whole lot of demonstrations. And yeah, you can see that for all the scores, this LIRA, which is the interactive method, is doing a lot better than the kinesthetic teach-in, which is just giving a whole lot of demonstrations beforehand and hoping that you covered all the situations you need to do. Okay, so that's the end of my presentation. No robotics presentation without a little video clip from a movie. This is from Real Steel, where you can really see how teaching a robot might be child's play if you have the right interface. And that's what I'm trying to work towards. Okay. So to sum up, I'll just sum up quickly, and then I hope there are a few more questions. So I hope I could show you a few examples on how doing this teaching interactively and intermittently can help speed up robot learning. I showed you a few different variants of using imitation learning or combining those demonstrations with reinforcement learning. And then, like I was saying before, there's still a lot of open questions. How do humans like to teach? And then especially for this audience, what I'm presenting is that actually meaningful human control. Yes, you can teach the robot to act like you want, so it's a form of human control, but then still there might be quite a few things you're unsure about, how it's going to generalize, how it's going to react in different situations where you have not taught the robot. Good.
Thank you very much, Jens, for this really interesting talk. So yeah, the questions are already rolling in. Carolina, if you want to ask your question, please go ahead.
Okay. Hi. Thanks.
Hi.
Okay. Hi. Okay. So thanks for the talk. It was very interesting. Yeah, my question goes, do you formally model any of these interactions or learning processes?
What do you mean by formally model?
So I just started my PhD on mental models in teamwork context. And yeah, so I'm looking for ways of modeling this team interaction to achieve a certain goal with context awareness and all that. And this is very interesting because this can also be seen as teamwork if you are to achieve a goal that both agree. So I was just wondering if you look at the knowledge-based models of any kind, or if you're just looking at more machine learning models and results. Not sure if you understand what I mean.
Not entirely sure. We'll see. That's a discussion. So we model these interactions indeed more kind of as a machine learning approach. In the reinforcement learning things I showed for those people that know reinforcement learning, the human kind of interaction was actually modeled as a form of exploration to be able to incorporate that in the reinforcement learning framework. for the other things, it's effectively some kind of a switch in the robot logic that tells it, okay, so here was an interaction, so I need to treat that differently. But we're not. So the robot itself knows about its behavior or its movements, where it's sure or unsure about what it's doing. So in that sense, it's modeled and taken into account, but really the interaction more kind of on a human level, that we don't model that very explicitly at the moment. But if you have ideas on how to do that and how that would be helpful.
Yeah, I'm wondering, yeah. For example, because, yeah, so I just saw for now, yeah, so this moment when the robot can detect that it's unsure about the box, for example, it stops for an interaction. And yeah, I was wondering if you have some kind of, if this is formally modeled in any way, so that there's actions and states, and it reaches that state, and then it stops and waits for the interaction, and then it goes back to. So how that's modeled? This was more my question, maybe.
So how is, I'm not sure if you're talking about the same kind of modeling. So
Okay.
what it does internally is it detects that in this case, okay, I still have two possibilities left, and the actions I would do according to each of them would be contradictory. So in one case I would move to the left, and in the one case I would need to move to the right. So it knows that there's a problem, and then there's a switch in the program that says, okay, now I'm going to stop and wait and request human feedback. And once I get the human feedback, and then hopefully it will allow me to choose the correct one, and then the robot can continue.
Okay, thank you. I will also think a bit more about it.
Yes, it's on my website, Akari. I can send it to you directly.
Thank you.
Great. Ah, Luciano.
Yeah, no one has. I have a. It's kind of a follow-up on a previous question, but it's on the point. So I just first wanted to understand if I got right. What is the trigger for the robot on the cucumber, like to define which when it should ask for feedback? And this, yeah, that's so two part. That's the first part, and the second part would be thinking about the context that the robot would be teaching another robot would be a similar point, and you say, okay, now I want to intervene because I see you're doing something weird or.
Yeah.
No, so first is what was the point? How do you define again the point that the robot asks for feedback?
Okay, so let's take this example again because it's a bit easier, I think. So what we already have is one demonstration, and then we can represent the movement in two different ways. One is relative to this coaster, and one is relative to the cup. So now we have two representations of the movement, and we don't know which is the correct one yet, because we only have a single demonstration. If we encounter the same situation again, maybe we just move the two objects together to a different location, and then the robot checks, okay, how would the movement look like if I move relative to the cup, and how would the movement look like if I move relative to the coaster? And if those are very similar, then you don't really care. You don't need to ask for feedback because you can just do it, right?
Okay, yeah.
Now, the other situation is I separate the two objects. And then again, if I predict how the movement is going to look like, if I move relative to the coaster or relative to the cup, then you're going to discover, okay, those are very different movements and they are not compatible.
Yeah.
And then the robot is going to ask for feedback.
Yeah, that's clear for me. But my wonder is like more about the intentions there. Like when you had this box with the cucumbers and the tomatoes, you don't know if you want like a specific absolute position or the other one. So that's
Yeah.
like even though the coordinates, everything's still kind of the same, but it's the intention for the human that you don't really know what was in.
So the intention in this case is also modeled as these reference frames, if you like. So the intention would be either move relative to the card with cucumbers or move relative to the world coordinates.
Okay, so it's still as a reference frame. Yeah, I understand that. So that could be, if there's a deviation from the reference frame, that's a good point of asking or giving feedback as soon as there is some deviation there.
Yeah. So in this case, we focused on reference frames because that's something that occurs frequently and is pretty visual. But I mean, you could do similar things also for other types of ambiguities. So in particular, what I'm interested in is force and position control, which is also, if you always have the same object, doesn't really matter what you do because one kind of results in the other and the other way around. So it's really about predicting different possibilities and figuring out if they are contradictory, which is what we call an ambiguity.
Yeah, that's great. Okay, and do you also?
See you, David.
Yeah. Okay. Thank you. Thanks.
So you had another question?
No, I think that's it. Let me leave also time, opportunity for someone else to jump in.
So just for my quick clarification for myself, Jens. So basically, so you could say more or less that, you know, one big issue in meaningful human control is that what if we misspecify the objectives of a robot or AI? Then, for instance, this resolving ambiguities would be one way, like that the robot would inherently stop and ask for feedback at the moment when it's not sure about what the objectives should be. Is that a correct? Would that be a correct extrapolation of this work?
I'm not sure, in the sense that if you misspecify something, I don't think the method I presented will solve that. Because I mean, if you explicitly specify, then the robot is going to be sure about it. What you could do additionally is that you allow also. So in the last part I presented, was effectively robot-driven questions or interactions. And the first part was more about human-driven interactions. If you assume that you have your misspecifications and you allow human-driven interactions so that the human can always jump in to change or correct or something, then yes, that might be a way to at least detect that something is going wrong and potentially also to fix it.
Thank you. So I think we have question for one more time for one more question. We're almost approaching 2 o'clock.
Yeah,
so
if there are more questions, shoot me an email.
Great. So if there are no more questions, indeed, yeah, I would like to thank you, Jens, for this great and interesting talk. It was very inspiring, and yes, and also thank to all the audience for being here and interacting with us and Jens. And yeah, we'll see you next time. Bye bye.
Okay. Thank you very much.
Yes. Thank you, Jens. Stop recording.